So hello everyone. So in the previous sessions we have been discussing about the probability. Now, if you remember what we have started discussion, we started discussion on what probability is, how to look at the probability, and then how to formalize, how to mathematically model a problem. So when you have a problem which involves uncertainty at that point of time, okay, how to model it. The steps I told you is the first thing I told you is to construct a sample space. Okay, when you have the sample space, then you can assign probabilities. Now you can assign probabilities to the elementary events. So what were elementary events? So each event in that, if it's a discrete thing, so you will assign probability to those discrete events. But we have also continuous probability. So the example over here, if you see in discrete probability, we had, let's suppose, a tossing of a coin, tossing a coin. So in that, our sample space was head comma tail. Okay. Then in this was our discrete probability. So discrete events when there were discrete events. So now we also had continuous events. So I told you, let's suppose you are playing a game. So in which if you are throwing a dot onto this, so you are playing that arrow game, you are throwing that arrow onto this. So let's suppose this is a unit square. Okay, if it is a unit square, so you can throw a dot in any point. Okay, if you drop a dot and in this point, let's suppose this is zero point 0.5, zero point 0.5. So the x-axis is 0.5 and the y-axis is also 0.5. So right now here you cannot assign probability to one particular point. The probability the point will hit at this point 5.5 is actually 0 because there are infinity number of points as such. So that's what I said, that sometimes if somebody says the probability is 0, it doesn't mean uncertain event. It does not mean the event won't happen. Okay, so if you take the example of this continuous event, now here you have infinite number of points in this, and this is uncountably infinite. There are two types of infinity. There is countable infinity. There is uncountable infinity. Uncountable means where you cannot put the mapping. Okay, and this is a separate discussion in itself. So, but remember that if somebody says that probability of an event is 0, it does not always mean that this event is uncertain. It won't happen. So this event is having 0 probability. It's impossible to occur. So this means this can occur, but maybe the sample space is not discrete. Let's suppose for this, if you just ask me what the probability that the dart will hit this point, I'll say 0 because this is a continuous and there are infinity points, and by definition the infinity, so we assign the probability to 1.0. So that's why we have assigned this probability area. We'll compute the area. So we'll say this area will tell us the probability. So it's a separate discussion. We'll have this discussion sort of thing. So the problem we're answering is if you are given a problem, how to now compute the probability. The first thing was to mathematically model that. In the mathematical modeling, we said that first see the sample space, and then when you saw the sample space, it can be continuous or discrete. Then assign the probabilities to the elementary events. So we're sort of restricting our discussion to this. So if you have discrete events, elementary event is one of the outcomes of the experiment. Then you will assign the probability to something. So if so, there we again saw there is something if all outcomes are likely. So we'll use the frequentist approach. That time we'll see what is the total number of outcomes possible in the sample space, and then we'll divide each element by that. Let's suppose head tail. Here we'll say that there are two possible outcomes, and if both of these outcomes are equally likely, we'll say the probability of this is 1 by 2 and probability of this is also 1 by 2. Okay, now we're assigning probability. This is the second step. So third step is that now you will have an event. Okay, you will have an event, and you'll have to also model this mathematically. What is the meaning of an event? So somebody will say, what is the probability of getting in head? This again is an event. Now for the event, you will compute the probability. We'll compute the probability. This is some sort of generic framework. Now I'll today discuss this. So today the first 10 to 15 minutes will be the discussion on the events. So how to mathematically capture those events if something is there by using the Venn diagrams and stuff like that. So if you are like previously we did some example where I said that Zubair is having two books and the probability of this and that, and then we said the complement and things. So all these things now we'll try to capture mathematically by using the Venn diagrams. So again, to just revise you a bit, a Venn diagram looks like this, where we represent the sample space by this outer circle, and if there is an event, this is our sample space which is represented by the square, and then if there is an event, let's call this event E, so we represent it by the circle within the sample space. Okay, that is by definition what event means, and this is the sample space which contains all the possible outcomes. So now there are different events in here. So there can be, the first thing that I'll tell about events is events can be mutually exclusive. Mutually exclusive means like these are two events where this E intersection F is phi. So they have nothing in common. So these are called as mutually exclusive events. So they exclude one. There is no sorry intersection. There is no overlap within these events. Then if somebody tells me what is the union of the event, so union means both of them will happen. Okay, so both of these will happen. So from that we have seen different sort of things, but now we'll see what is called as algebra of these events. So algebra of events. Have this heading into your notes. Write it as algebra of events. So the what is the algebra of events? This basically is a translation of whatever is asked to you in some language, in English language, and you will translate it into mathematics. Okay, or vice versa. So you will. This is basically a translation of English into mathematics. So you will be asked a question and you will have to answer this in somehow. You'll have to answer, okay, now probability of this and that, and you will assign these values or these variables to these big sentences. So there is where this algebra events will be helpful. I just gave it a separate heading so that there is very less problem for you guys when you are doing the questions or when you are just solving any real world problem, so that you know that for this sentence I'll assign this variable. Okay, we'll have this. Let's suppose we have this S and we have this event E and F. So if I have the first thing that I'll translate, the first thing is probability that A does not happen. So first is probability of, let's call this A and B, so it will be easy for me also. So A and B. So if somebody says probability of A, so this is in mathematics we'll write it like this, probability of A. So the second thing is probability of A does not happen. So probability A does not happen. So this will be just a complement of this. So this is probability of A complement. So what is A complement? So A complement is what's outside A. So this portion. This Venn diagram is really useful when you are solving questions. I'll show you that in a, I think in next couple of minutes. So the third thing can be, let's suppose if you have probability, both of these will happen. Like both of these will happen means A will also happen and B will also happen. Probability both the events will happen. I'm just showing it in two events, so you can extend it according to your ease if there are 3, 4, 5 events. So what is the meaning of this? So this means probability that A will happen and B will also happen, and means intersection B will also happen. So this is the probability of that. So if again you have to see it in the Venn diagram, so then we should have some event which has intersection. So if A and B, if both are happening, so that means something like this. So if A is happening and B is also happening, so this is the intersection part we'll see. Okay, if we have probability of A or B, so either one of them should happen, or A should happen or B can happen. So the fourth I'll write is probability A or B. A or B happens. So what is that? Probability A or B happens, that means this union. Okay, whole of this union. So A will happen or B will happen. So why am I showing you these sort of things? Because we'll derive all the formulations based on this. So whenever you know what is the probability of A or B, that means probability of A union B. I'm talking about union. A happens or B happens. If I saying both happens, that is A and B happens. So I'll write it and like this. So A and B happen. Okay. So this will be like this. So this is A intersection B. So now if I say that A happened but B does not happen. Okay. So I'll say, let's suppose probability of A will happen and B does not happen. B does not happen. So in the Venn diagram, we'll see it first. So this is our event A and this is our event B. So I'm saying that A will happen, but B will not happen. So what's the meaning of that? That is A will happen and what this is the whole B. If you see, this is our whole B. This is our whole B. Okay. Now I'm saying that A will happen. So whole of the A I'm talking about. Now I'm saying B will not happen. So that means this should not happen. So I'm saying A will happen, B should not happen. This is only this portion in the Venn diagram. So what does this portion represent? It represents A will happen and B will not happen. So this is B complement. So B complement is everything outside of the B. Okay. So everything outside of the B is this. So I should change the color. So everything outside B is, so everything outside B is this. Okay, even this. This is everything outside B. So when I'm talking about A intersection B complement, that is this portion now. Only this portion will remain. This crescent portion. That's the meaning of this. If A will happen and B will not happen. So that is A intersection B complement. Okay, so I can write it in some other way also. So if I am saying probability of A intersection B complement. So again, the meaning is that A will happen and B will not happen. So I can write it like this. I can say the probability of A. Okay, take the whole A now. Take the whole A, making this diagram again. So take the whole, this is our sample space. Let's suppose this is our one event A, this is our second event B. I'm saying probability of A, take the whole A now. Take this whole A and subtract this portion. Okay, subtract this portion. That means minus probability of A intersection B. This is one of the identities that we'll be using. I don't want to memorize you. That's why I'm showing you these pictures. But rather than these, like in many courses or in many books, you will see the mechanical formulas. You'll see probability of A intersection B complement is this. So you need not to memorize, just have this in your mind. Probability of A intersection B complement is this portion. You are computing this, only this part. So now what I'm saying is, you can compute it like this. Have the whole probability of A and then just remove the portion probability of A intersection B. So you have to remove this and you will get this crescent portion. So this is our fifth property. Now, if I say probability A does not happen, but B happens, just the reverse of that. Probability A does not happen. That means A should not happen, and B should happen. This is like this. So in English, I'll say probability A does not happen, and B happens. Because some event will occur, happen or occur, I'm just using them interchangeably. So again, if you see the same diagram that we had, so this is our event 1, this is our other event. So this is our A and B. So I'm talking about this portion. This is what this is the portion I'm talking about, because here you see that A complement intersection B. So A complement is everything outside A. Okay, then intersection, what is the intersection? So where is the overlap between that? So this is our A complement is like this. If I make the A complement, this is A complement. So this is whole sample space, and except this portion. So except this portion, this whole thing is my A complement. Okay, this is my whole. Now I'm saying A complement intersection B. So what is B? So if you now take the B, B was this much. So this much was the B. Okay, what is the overlap? So overlap between these two is, so overlap between these two is this much. So just take it out. Okay, and this is the overlap between these two. That's what I'm saying. A complement intersection B means take everything what is outside A. Okay, I think A complement was something like this. This was A complement outside A, and then we had this was our B. This was our whole B. This thing was our B, and this, if you see over here, this portion is the complement. This portion. This is what I'm talking about. This A complement intersection B. So this is A does not happen but B happens. So again you can see the formula. A probability of A does not happen but B happen. So this will be equal to, take the probability of B, because we are computing the probability of this much. So you are computing probability of this portion. Okay, so what is the probability? Take the whole B and then subtract probability of A intersection B. So this is our A intersection B. This point is A intersection B. So there are some more properties. So other properties that we'll see. Hmm. Probability at least one of A or B will happen. So probability, I write it P, at least one of A and B will happen. A and B happens. So what's the meaning of this? So I mean either A can happen or B can happen or both can happen. So the meaning of that is A union B. So this is what I mean by A union B. In the Venn diagram, it will be like this. So if you have event A, you have event B. So A and B. So this is A union B. Okay, so now we have derived this formula, so we'll see it, can we just approve it from this. So we have derived it by using these three axioms of probability. Now we'll see it from the Venn diagram. So probability of A union B. Now if you can see is, this is probability of A, take this whole A, so I'll write probability of A plus probability of B plus probability of B. Okay, now you know that there is some overlap. So if you see this part, if you see this portion, it is counted twice. It is counted with A first and then with the B first, but I just wanted to count it one time, so I should subtract it with one time, probability of A intersection B. That's what we derived the formula. We derived from the axis of probability. If you see the from the Venn diagram, it looks pretty clear. So I'm taking the whole A first, then I'm taking the probability of whole B first. Then what happens is I'm overcounting this portion. I'm overcounting this A intersection B. That's why I'm just subtracting it once, because I just need it once. I just need it to compute once. But here, if you see it, I have computed twice. First in A, then in B. That's the reason I'm subtracting it one time. Okay, is it clear?
Yes, sir.
Okay, just keep your focus, because this might sound a little bit boring, but these are the rules. You must know how to translate these things. And then we said probability exactly one of the A and B happens. So probably one of them should happen. So this can be like this, probability exactly one of them happens. Exactly one of A and B happens. So by that I mean, so either A should happen or B should happen. Both should not happen. So in, if you see it in probability, how do you write it? You write it probability of one of them should happen. So either A should happen, B should not happen. Okay. So probability A should happen and B should not happen, or means plus. So our probability A should not happen, B should happen. So in the Venn diagram, if you see it like this, so this is our Venn diagram. So I'll make it a little bigger. So this is our Venn diagram. So we have these events A and B. Now I'm saying either A should happen or B should happen. So this means the probability of this portion means this much. So this is our event A, this is our event B. So probability A should not happen, then B should happen. This is this much. So this red portion over here is A intersection B and union A intersection B. That's what we are computing the probability of. Okay, now if you have to compute the formula for this, so how will you compute it? So I'm saying the probability of A union B complement plus probability of A complement intersection B. So just see, you have to compute this much, this and this. Just see how we'll do it. So we'll compute the whole probability of A. Okay, then add probability of B. Now we do not want this intersection part. We do not want this A intersection B. But in probability of A, it was computed once. In probability of B, it was again computed once. Now we don't actually want that. We'll remove it two times. Is it clear? Is this formula clear?
Yes, sir.
Now you can see that we don't memorize the formulas. You can clearly see we are not memorizing these formulas. You can see in the books; they are written in the books. But if you just make a Venn diagram, it will make your life easy. You can just derive these formulas on the fly, and even you can tinker with these formulas and come up with some other formulas. Okay. Now we'll see some other properties. Neither of them should happen. So that's the question that we did in the previous class. So we said probability neither A happen nor B happen. So neither A nor B should happen, nor B happens. Let's suppose. So this means that A should not happen and B should not happen. So A does not happen and B does not happen. So this can be written as probability that A does not happen and B does not happen. Again, seeing it in the Venn diagram, the diagram that we have. So why does it lie? So we'll see it in the diagram. So now I'm saying A should not happen. A means that A complement, and this is what is outside A. Then B complement means what is outside B. So what is remain then? So what is the overlap between these? The overlap is this outside. Convince yourself of this, that the outside portion, this red portion, is A complement intersection B complement. So do you agree with this? So first see it. The overlap between A complement and B complements whatever is outside this A union B. So that's what I wrote. You can write probability of A intersection A complement intersection B complement. This is equal to probability of A union B whole complement. That's where this is now De Morgan's law. You can just write the complement. So we'll not, in this dash we'll write complement. So again, De Morgan's law says the same. A union B complement is A complement intersection B complement. Okay, so here you can get the De Morgan's law also. So from just by looking at the Venn diagram. Again, one more thing that you can get, if somebody says what's the probability of A complement intersection B complement. So for complement, I'll use dash, C, or this bar. So these are three symbols I can use for the complement. So then you can directly write it again. If you see it over here, this is 1 minus, this is sample space, probability of sample space, and then minus this event. So I can write it probability of sample space minus probability of A union B. So this is our union. So this is our union, A union B. So this outside is a sample space minus union, but you know the probability of sample space is 1. This is minus probability of A union B. You can write it also like this. So these are the formulas that you can just derive by seeing at the Venn diagram. So if there are complex events, and most of the time is when you are solving something, there will be 2, 3, maximum 4 events happening. Okay, there are 4 variables where you have to take care of, and you can easily track this Venn diagram, and you can come up with the answers. Okay, and for this I'll make a diagram for 3 events, and then you can, these are 3 events. Let's suppose this is our event 1 A, this is our event 2B, this is our event C. This is A, B, and C. Now I want you guys to help me out. Okay, I'll ask you guys first. I'll ask Asra to help me out. So what can I name this event? So this event, blue color event. So what should be the name of this event?
This is, sir, probability of A
A.
minus probability of A intersection B
Mm-hmm.
minus probability of A intersection C and minus probability of the intersection of all the three.
Can I just say that this is probability of A and there is no B involved and there is no C involved. So I can write it like this. Convince yourself of this. So I'm saying this portion, if you see this portion. So this includes A. Okay. So what is the intersection of B complement? B complement means everything that is outside B. So outside B is also this. So and other things. Okay. So what is outside C? Outside C is this and other things. But if you see the intersection is this portion. So this can be written as this portion. So this is written as A intersection B complement intersection C complement. See it in the Venn diagram. You should be able to see it. Are you able to see it? That's why I'm just giving you 1-2 minutes to just understand this. So this portion, if you see, is A intersection B complement intersection C complement. So there we have A is involved there, but there should be no B and there should be no C in that. That's why we have named it as A intersection B complement intersection C complement. How many of you are seeing it? Okay, I think most of you guys are now convinced that this is. So what about this now? What about this portion then? So I'll ask Amir. So what is this? So this portion only. I need this portion.
Sir, B intersection
B
uh, com
intersection
C and B's complement.
A complement intersection C complement. So this is
Yes,
this
sir.
portion. Okay. So what about Rian? What about this?
Sir, C intersection B complement intersection uh, A complement.
Right. So again, help me with this, Rian. What is this portion? So this over here. This lies in A and C. If
This
you see
lies
the.
in A and C.
A
If you
A intersection A intersection C
Mm-hmm.
Mhm.
intersection B complement.
Right. Okay, Jahangir, help me with this. I think he's yes, yes. What is this portion I'm talking about? Maybe Zakir, you can give the answer, and for Jahangir, will ask for this. Jahangir, you keep the answer for this ready. Zakir, what is the answer for this?
Sir, A intersection B intersection C complement.
A intersection B intersection C complement, because C is not there. So what about this, Jahangir, now? No, you are not audible. Okay, maybe Zakir, you can help me out in this also. So what is this?
Intersection B intersection A complement.
This is C intersection B intersection A complement. Okay, so what about this now?
A intersection. So which one? Middle one.
Intersection of all of
A
these, huh?
intersection B intersection C.
The
Yes, sir.
middle one, this portion. Okay, now you can easily identify. If you have events, you can easily identify from that, okay, what event belongs to which. Now I have shown you one more formula. We have seen that yesterday, I think. Probability of A union B union C. The formula for that was probability of A plus probability of B plus probability of C. I think you remember this. Then minus probability of A intersection B minus probability of A intersection C minus probability of C intersection B plus probability of A intersection B intersection C. So this was the formula for that mutually inclusion exclusion principle, which we I just saw there. So I said this can be extended to any events also. Let's see it from the Venn diagram now. So I'll just erase it and we'll make the Venn diagram to compute this formula. I don't want you to memorize any of the formulas. It should be easy for you to just compute them on the fly. Okay. Now this is A, this is our B, and this is our C. The thing that I want to compute is this. Okay, this is the thing I want to compute. This probability of A union B union C. This is equal to the initial thing that I am saying is add all the probabilities. Probability of A plus probability of B plus probability of C. Now if you see in here, so if you see this portion, so I'll just erase these lines. So if you see this portion, so what is this? This is A intersection B. Okay, so this is just A intersection B, this portion. Just remove the C for now. So now if you see it, how many times did we count it? So it was counted in A, it was counted in B. Okay, because we took the whole A, whole B. So we'll subtract this. So we'll subtract probability of A intersection B. Okay, now think about this. This is A intersection C. This was again counted 2 times, once with A, once with C. So we'll remove it also. So we'll remove probability of probability of A intersection C. Then now think about this. Think about this. This over here is B intersection C. It was counted once with C, once with B. That's the reason we have to remove it probability of B intersection C. Okay. Now one more thing. If you see this portion, if you see a smaller portion, which is the intersection of all of these, it was counted one is in this, then in this, then in this. Then it was removed from this, from this, from this. Okay, but still we need to count it once at least. That's why we'll add it one time. So how many of you are able to understand this? How did I derive it from the Venn diagram? Okay, I'll repeat for the others. So what I did is, so I said these are 3 events. So if probability of A union B union C is the that is the whole of this. So where I am having this pointer. So now what I'm doing is I'm adding the probability of event A, B and C. Now if you see in the diagram itself, so this A intersection B, it is over counted once. So I'll subtract it once. Then you see this A intersection C, it's again over counted once. So to balance it out so that it just gets counted one time, I'm subtracting it. So for this B intersection C, same thing happens. But now because we have this portion, this yellow, so the intersection of all of these 3. So we counted it here, we counted it here, counted it here. So now we subtracted 3 times also. That's the reason I have to add it one more time. Okay, so even probability of A union B union C union D can also be computed from this. So now you see, so how many combinations will be possible? So this will be probability of A plus probability of B plus probability of C plus probability of D. Now we don't even need to look at the diagram. So I am saying the first you should add all the prob, then you should subtract the 2 terms. So how many 2 terms are possible? So I'll write it here. A union B union C union D. Okay, so I'm saying that add all the probability, summation of probability of, so all of these events which have one of these, let's suppose A, B or C, D. So I'll write it as E1 E2. Let's write it as E1 union E2 union E3 union E4. So I'll write summation of i's 1 to 4 probability of all of E i's. Okay, then what to subtract now? what should I subtract? So I should subtract these two terms. So how many two terms will be possible? So out of the four terms, I'll have to choose two terms. So that means 4C2. I think it will be 6. So I'll have probability of minus probability of E1, E2. So this intersection in between. So I won't write intersection. Minus probability of E1, E3. Minus probability of E1, E4. Okay, minus probability of E2, E3. Minus probability of E3, E4. Just see if I'm overcounting. E3, E4. Minus probability of, so 6 should be there. So 4, 3 is also there. So
E2, E4.
E2, E4. Okay. So these are the probabilities. Now I can easily count these things. So why are these number of terms? So this is 4C2 number of terms. Okay. Now I'll add. So what I'll add 3 terms. So this should be 4C3. Okay. These many number of terms will be there. Then at the end I'll just add this. So I'll again subtract the last one, that is probability of all of these. Probability of E1 intersection E2 intersection E3 intersection E4. Okay, so how to count this? Like E4, there will be 3 terms now. E. So this will be 1, 2, 3 plus probability of E1, E3, E4, and what is the last term? Probability of E2, E3, E4. Okay, and this will be subtract, and you have to alternate it. So you can even prove this by induction also. Now this is clear from the Venn diagram. How many of you how many of you will be able to prove it for the n? So I have even wrote that formula, I think, in the previous session, but please try to capture this through the even through the Venn diagram. I just try to generalize this and then prove it by mathematical induction. So you can prove that by mathematical induction. Okay. So these are the formulas that I wanted you folks to at least know, because whenever you are solving any problem, that time you must know all of these things. It makes mathematical modeling easy. We had discussion over it. If you again see the bigger picture, this was our bigger picture. So we wanted to know about the events now. So if given events, if we are given the events, and then how to compute this. So that time it will be really easy for you to sort of understand these and mathematically model these things, and then you will compute the probability for the 3 events, 4 events, something like that. So I hope that now you have the necessary skills by which you can just compute the events. If you are given a question and you can compute the events. So just I'll write types of events that I just said. So that again can be written as a heading, types of events. Okay. The first event I'll write is mutually exclusive event. I already said you that, but still you should have the note of these things into your notes which you are making. So mutually exclusive events. So what are these? So if there are events which have nothing in common, so they are disjoint sets in terms of set theory. So this is the one event, this is the second event. So here we can say that E intersection F is phi. So these events are called mutually exclusive events. Okay, so that means if A and B, they cannot happen simultaneously. So I can write E and F cannot happen simultaneously. Cannot happen simultaneously. Okay. So let's suppose let me give you an example. I'll tell you to say which are the mutual exclusive. Let's suppose we are throwing a dice, throwing a die, throwing a die once. Okay, let's suppose E1 is our event in which I'm getting an even number. E1 is getting an even number. Getting an even number. Let's suppose E2 is getting an odd number. Getting an odd number. And E3 is getting a prime number. Okay. So which of these events are mutually exclusive? So can I say that E1 and E2 is mutually exclusive? Amir, starting with you.
Yes, sir.
So why are they mutually exclusive? Because if it's even number, if it is not odd, then that's what, like, if an event happens, if an elementary event is this in even, it will not be in E2. So if you just enumerate these, so even numbers will be 2, 4, and 6. So odd numbers, if you enumerate, it will be 1, 3, and 5. Prime numbers will be 2, 3, and 5. Okay. So E1 and E2 are mutually exclusive. So E2 and E3, are they mutually exclusive?
No, sir.
They are not. So this is the mutually exclusive events. So many people get confused sometimes with independent events, but in gain this in your mind, so we'll speak about independent events also. So in the coming when we are discussing about conditional probability based theorem, and then, but I want your basics to be really clear before releasing the assignment, and before attempting the questions or coding some things. You must be clear with these things. So second type of event I'll write is exhaustive events. Exhaustive events, they're just names. So what are exhaustive events? Let's suppose we have a sample space. Okay, so sample space, if there are events, let's suppose this is event 1, then this is event 2, let's suppose this is event 3, this is event 4, and this is event 5. Now you saw that whole of the sample space, if I take all of these 5 events, so they make up whole sample space, then I call these events as exhaustive events. So, okay, so events a, e1, e2 up till en are called exhaustive. If I take union of all of these events, if I take union of all of these events, so they will be giving me the sample space. They are called exhaustive events. Okay, so now if I am giving you head and tail, so this is these two are exhaustive events for the sample space of tossing a one coin. Okay, these are exhaustive events. You will see these terms frequently. Are these exhaustive events, or these not exhaustive events, and things like. Then we have equally likely events that we had discussion on. So then we can have equally likely events. So in which the events are equally likely, and we have in case of fair die, let's suppose each number appearing, each number on the die, it is equally likely. So they are called as equally likely events. So we'll give the probability based on total of the elements in the sample space. Okay, if we have this roll of die, so this is 1 2 3 4 5 6. So there what we'll do is, if while assigning probabilities, you will give 1 by 6 to this, because number of elements is 6, and you will do element divided by the number of elements. So we have this element, this is 1, and then we'll say number of elements in the sample space. That is the probability of each elementary event. Is it clear? The question is that we have probability of an event A is 0.25. Okay, probability of an event B is 0.5. Probability of A and B, A intersection B, this is equal to 0.4. Now the question is that find the probability that neither A nor B occurs. So you will have to find probability neither A nor B happens, nor B occurs. This is first thing, and also find probability of A intersection B complement. Find these two. The question was the probability of A was given, probability of B was given, and probability intersection B. The first thing is we have to find probability neither A nor B happens. That is, we have to find probability of A complement intersection B complement. So that's what we have to find. So I know that this is equal to 1 minus probability of A union B. A union B. This is the probability, and there you will see that what is this 1 minus this is 0.61. If you just compute it, this is 0.39. Okay, I think this is the answer. And even you can, even if you do not remember this, you can just create a Venn diagram like this. Just create a Venn diagram. You have this, then you have this. So here you will write 0.25. So this is, here you will write 0.14. Then here you will write 0.5. So 0.5 and then 0.14. It becomes tedious to write it here. So this is what you have to write. Now you are computing neither A nor B. That is the outside portion that you have to compute. This portion. This means you have to compute probability of A union B first. Compute this. So add these and subtract this. So this is 0.25 plus 0.5 minus 0.14. Okay. So this is what is equal to 0.61. Then you know that the whole sample space minus this is gives you this. So this you can say probability of A U, that is what I said. 1 minus 0.61, that's equal to 0.39. Okay, now I'll ask Asrar to run me through the second question. Probability of A intersection B complement. So how did you solve it?
It will be, sir, probability of A minus probability of A intersection B.
Beautiful.
Through Venn diagram, we can easily do it.
So you can easily see it. This is the portion that we are interested in. So probability of A is given to us, and probability of intersection also B is also given to us. This comes out to be 0.11. Now let's level up a question a little bit. Now the thing is, you have to compute probability of A complement plus probability of B complement. This is what you have to compute. This is question. And probability of A union B is given to you is 0.6. probability of A intersection B is given as 0.2, and these are two things that you are given. Yes, and then you have to find it.
Probability of A union B is simply probability of A plus
Is equal to
probability of
probability
B
of A
intersection
plus probability of B,
plus probability
then
minus
minus probability of A intersection B.
probability of A intersection B.
Okay, then
This means simply 0.6 equal to
this is equal to
0.6. Sir, I mean 0.6.2 equal to probability of A plus probability of B.
so this is 0.6 and this is 0.2. I'm just putting the values what you are saying, huh? Plus probability of B minus, so this means this is 0.8, this is probability of A plus probability of B. Now the point is we have to find the probability of A complement and B complement. So I assume that what you did is 0.8 is 1 minus
1
probability
minus
of A complement plus 1 minus probability of B
plus 1
complement.
minus probability of B.
Okay, so we'll shift it from through here, then we'll say that probability of A complement plus probability of B complement, this is equal to 1.2. Okay, I hope that everybody was able to do this. So everybody understood this?
Yes, sir.
Okay.